Hi, welcome to Happy Browser, Happy User. First I have to say thank you, my amazing, talented husband drew these pictures for me. I'm trying to get him to open an Etsy shop and start selling his illustrations more, so fingers crossed. I'll tell him you like them. Anyways, Mina stole all my thunder. Yes, hi, I'm Katie Sylor Miller. I work at Etsy. I worked on the Design Systems Handbook. I made this stupid website called Oh Shit Git, which strangely went viral. And I actually had the privilege just this past fall of collaborating with Julia Evans of the Wizard Zines to create an Oh Shit Git zine. The URL to go buy it on Gumroad is right there. So in the performance community, you hear this phrase a lot. Performance is UX. Now, I don't have to justify this to any of you, thankfully, because you're here. You know that this is the case. We all know that better performing sites provide a better experience for our users. But I want us to break this down a little bit farther. So let's start with UX. Now, we know what UX means. That means providing a better experience for our users. But this term, performance, this is a lot more complicated. It's this big, huge umbrella term that covers like a ton of different topics. And I don't know about you, but when I first started learning about it, I was like sitting in the audience like you are, wondering, okay, how does all of this fit together? And after I was here last year, I did a talk that was archaeology themed, of course, about my team at Etsy, how we went and improved the performance of our mobile listing page. And when we got back to Etsy, a bunch of engineers were like, sweet, write this up. We want to do this too. Like, teach us your ways. But I couldn't teach them anything without first teaching them how do browsers work. None of it made any sense unless you had like a pretty good knowledge of like the inner workings of the browsers. So really, when we're talking about performance, what we're talking about is making the browser happy. How many of you, though, actually like learned in school or in your code boot camp, or you had a thing at work that taught you how browsers work? And Addie, do not raise your hand. Yeah, see, not a lot of people. This is not something that we learn about, but it's so fundamentally important to how the web works that I think we need to talk about it more. I think it's really telling that I'm probably like the 6th person to come up on stage today and talk about, let's show you how the browser works, because it's that important. So let's really know how the browser works. But first, to understand how we're going to make the browser happy, we have to know what makes the browser sad. Poor browser. So really, all of the stuff that we talk about when we talk about performance can kind of get bucketed into these two different things, these two problems we're trying to solve. The first one is network latency, so the fact that, like, hey, it actually takes time to transmit bytes over the air into computers. How do we work around that and make that happen as quickly as possible? And then the second problem that we do a lot to work around is this mostly single-threaded nature of the web. The browser main thread, it's like a working mom. It does everything. So we want to try to relieve it of some of that extra work. Cool. All right, so let's understand how all of these pieces fit together. And we're going to do that classic interview question. What happens when I type a URL into the browser? Oh, is it? Oh, wrong button. Boop, there we go. So the website we're going to go visit is a tribute to the absolute best cat GIF ever of all time, mindblowncat.com. Yes, I did go and buy this URL, but please don't go and look at it because you're going to ruin the big reveal at the end of the presentation, so don't ruin your awesome surprise because you're going to be really excited when you see this. All right, so the first phase of how browsers work is navigation. Now, navigation is actually completely opaque to our users. They have no idea that this is happening under the hood. So what we really want to do is get it over with as quickly as humanly possible. But there's a lot of things that are going to try to prevent us from doing that. The first is mobile networks. So if you're on a mobile phone and you're not actually connected to Wi-Fi, every single request that you make to the internet actually first has to go off to a cell tower, which then passes your request to like the real internet. So that makes everything a little bit longer. Now let's say I'm going to go to this website the very first time. I've never been there before. The first thing my browser has to do is figure out what's the IP address, which it does by going off through a series of steps and various layers to get to a DNS server, which then returns an IP address to us. All right, so now that we know that the server is located at that IP address, we want to set up a connection to the server. And the way that we do that is via what's called a TCP three-way handshake. So far we're at 5 steps, and we haven't gotten any data back. And then next, because we're being good citizens of the net and we care about security, we have to do, whoops, I pushed the wrong button again. All right, we have to do an SSL handshake, which is actually 5 steps. And then, once we have our SSL connection set up, we can finally send over our poor little HTTP GET request, which then gets over to the server, and the server does its server stuff, and then it puts together a package of HTML and sends it back to our browser. Yay, so now we finally actually have some data in the browser. That's our time to first byte, and now that we have the data, we can start to parse it. Now, one thing I want to note, you'll notice that there's these multiple lines. So this represents what's called TCP slow start. How many of you have heard of the first 14 kilobyte rule? Cool, awesome, yeah. So the reason for the first 14 kilobyte rule is because TCP congestion control algorithms start by sending out 14 kilobytes worth of packets. Once it knows that the network can handle the load, it will start doubling the size. Cool, all right. So, how much of all of this do we control? The answer is very little. I mean, and honestly, the fact that all of this happens in like a few hundred milliseconds is like, computers, they're amazing. So if we can't change a lot of how this works, what can we change? Well, one of the main things we have control over is that little server time there. But some things that we can do, so Pat Meenan actually stole a lot of my thunder, told you a lot of these tricks already, so I'm just going to kind of breeze through most of them. We can use H2 push to serve resources out sooner. We can use preloading and resource hints. We can reduce our server response time. Now that's the main thing, again, that we have complete and utter control over. We can use caching. We can serve statically loaded resources. Every single thing that you can do to get that data out of your server faster, the better. You can use a CDN, which typically is good because they're located geographically all over the world. So wherever your users are, they're probably going to have a server that's closer to them. Obviously, smaller files, everybody's talked about this. The smaller your files are, the fewer round trips you have to make, the sooner that the information gets to your user. And then again, our friend, the first 14 kilobytes. If you can get everything that the browser needs to start rendering a page, or at least part of it, like Pat was saying, get all of your CSS, and then get most of your body, or at least some of your body, and the browser's going to try to help you out and start rendering things sooner. All right, cool. So let's check in. We're doing awesome. That spinner keeps going. Great. So let's move on to parsing. So parsing is the step where the browser takes all of those little text files that we sent over and turns it into something that the browser can actually work with. Namely, the DOM and the CSS-OM are the two things that we want to get to. Because again, the DOM and the CSS-OM, you put it together, the browser can actually render something on screen. We want to do that as fast as we can. All right, so let's see how this works. Now, our test file that we're going to be using is like dead simple. Unfortunately, none of us actually get to do something like this for our day job. And if you've been paying attention, you probably already see a bunch of things that I did wrong that we're going to need to improve. And this is a bad idea. But I want us all to really understand why this is a bad idea. All right, so we're going to start building our DOM, our document object model. So the DOM is pretty cool. It's like both the internal representation of the markup for the browser, and it's also what's exposed to us via JavaScript so that we can actually interact with the elements on the page and like do cool stuff with them. Although not as cool as the stuff that Sarah was doing with SVG. I can't even begin to imagine how you do that. So, all right, where we left off, our network had returned with HTML, and now our main thread, our poor, sad, overworked main thread, is going to start going through each of these elements and lines. It kind of goes through this whole process called tokenization to figure out like where does a HTML tag start and begin. So it takes that first tag HTML and it creates the first node in our tree. And then, oh, wait a second, a new friend has appeared. The preload scanner. So this was something Pat also mentioned. While the main thread is off parsing the DOM, browser manufacturers have done this really super cool thing to make our jobs easier, which is this preload scanner that's going to continue to parse through your DOM and find all of your high priority resources like CSS, JavaScript, and images, and start to go off and make the network call for those for us before parsing is complete. So it means we're going to go off and get that important style sheet like way faster. Although not really in this case because it's like just down one. All right. Oops. And then we get to our CSS. The request has already been made, but like Pat said before, we can continue parsing after we hit CSS, so that's great. And then we get to our script tag and we're stuck because JavaScript is render blocking. When you include it without the async or defer attributes, which we didn't, so that was our bad idea number one. But first, we have to go and process our CSS. CSS blocks JavaScript because when you think about it, how many times are you going in with your JavaScript and trying to query CSS properties on elements? So the browser knows, okay, and to avoid a race condition, I'm going to stop and wait for the CSS to be ready before I create the JS. So let's go make a CSS OM. Yeah, the CSS object model. It's very similar to the DOM. It's another tree. Really, browsers are just like trees all the way down. You're going to get really sick of looking at trees. I'm sick of talking about trees because Git is also all trees all the way down. Can I say I like trees? I don't know. All right, so we go through each rule set in our CSS, and we're going to create this tree of nodes that have a parent-child relationship based on our selectors. Anything that is a single selector is going to go in as a child of the body. So you can see our h1 and our .title class are direct children of the body, but that image is a child selector, so it's a child of the .border. Cool. All right, Marty, let's go back to the DOM. Sweet, so our CSS is done, and then while we were off building that, our JavaScript file came back over the network. Yes, so we can move on. We can parse and execute our JavaScript. So the first thing we have to do, though, is we have to make another tree, an abstract syntax tree, which I can never say, so just say AST. I don't think anybody can say that without tripping over it. And the AST actually is really bonkers, so I'm just going to like breeze through this animation because I made it and we don't have time to go through it individually. But what you should really do is go to astexplorer.net and type some JavaScript into the editor, and you'll live update see what the AST for that JavaScript looks like, because it's actually really, really cool, and it really shows you like the fundamental constructs of JavaScript as a language. So highly recommend astexplorer.net. All right, we have our AST, and now what happens next when we want to actually like interpret and compile and parse interpret and compile all of our JavaScript is like a little bit different between browsers. And what Addie showed this morning, actually, what I'm about to show you was wrong for Chrome. I apologize. You threw me under the bus, but that's okay. Anyways, yeah, so long story short, most all of the JavaScript engines do some version of taking that AST, passing it into an interpreter, which then outputs bytecode, which can then be executed on the main thread. But bytecode outputs JavaScript. It works really quickly, it outputs stuff quickly, but the bytecode that it outputs executes somewhat slower. So most JavaScript engines do some sort of version of passing the bytecode off to one or more optimizing compilers, which then takes a little bit longer, but the code that it outputs is optimized so it executes faster on the main thread. Now, there's a lot more to dig into here, and there's a lot of details about like what kind of code works well with the compilers and what doesn't, but like in the interest of time, we're going to just kind of gloss over that, and you can learn about it if you're really interested in JavaScript compilation. Cool, all right, so let's execute our JavaScript. Oh, womp, womp again. We threw an error. So, uncaught type error, cannot set property src of null at bad idea script.js line 5. So line 5 is that cat.src. So why is that null? Well, remember where we are, where this JavaScript is executing. Our DOM looks like this. Is there any element in our DOM that has the ID of cat that getElementById is going to find? No. So this is why things like the old school like jQuery.ready handler exists, is it's to make sure that you're not actually executing your JavaScript code and looking for things in the DOM before they're actually done out by the parser, because the parser has to stop and wait for JavaScript to execute before it can actually parse the DOM. So this is like a cool little fun fact, and you know, I think most modern frameworks that most people here are probably using automatically take care of this for you, but it's cool to know. Cool, all right, Marty, back to the DOM again. Sweet, so our JavaScript is done. We are ready to move on. So the main thread goes back to parsing through each element and generating our tree of nested parent-child nodes that represent our nested HTML. And one thing I want to point out here, I don't know if anyone noticed in my HTML, I didn't add a closing tag for my p tag, and that's okay because the HTML parser is like super fault tolerant. It's going to let you make mistakes, and it's going to try to fix them for you, but just be careful because it might fix it in a really unexpected way. So you're really much better off, and you're going to make the parser happier if you actually validate that all of your HTML is like nested and closed properly. It will let you get away with it, but you shouldn't take advantage of the browser like that. Cool, all right, so we're done with parsing. And there's actually a lot of things that we can do to make that better. So let's go see what we did. And just as a reminder, what we wanted to do was get to the DOM and the CSS-OM as soon as possible, which we didn't really do a spectacular job of. So this is like a timeline of what we just did. You can see there's our main thread and all of the actions it took. Our worker thread, which could be any one of a number of different kinds of threads, and then our network process. And you can see there's a bunch of places where we have to actually stop and wait for other things to happen. This is really not ideal. So how are we going to fix this? Well, first things first, let's think about our first 14 kilobytes. We're not really sending a lot of CSS over, so let's just embed it directly in our head. So what does the effect of that? So now you can see our period of waiting is much shorter because we don't have to go off and wait for that CSS to come back over the network before we can start parsing it. However, there's still that block of time where we're waiting for our JavaScript to come back. So that worked really well, so let's just do it again. Let's just dump our JavaScript into the document, but this time we're going to follow that best practice and we're going to put it at the bottom of the body. Now great, this is way better, right? We're not really hanging out and waiting. So we parse our HTML, we pause, we parse our CSS, we parse almost all of the rest of our HTML, basically the entire body. So at this point, the browser could actually go off and start rendering this for us, even though parsing of our JavaScript is incomplete. But it's going to try to help us. And then we just have that tiny little bit where we parse out the closing tags of the body. But we can do even better than this. We can use async and await, right? Or excuse me, async and defer. So here's what happens when we async our scripts. So async actually will go off and request a script resource, and it will not pause when it gets to the script tag, but it will keep going and then wait until the JS file comes back, and it will stop what it's doing, and then it will parse and it will execute our JavaScript, and then it'll go back to the DOM. Now in our case, this actually kind of made everything worse because we have like a really small JavaScript file and it came back pretty quickly. However, if we have a really big JavaScript file or if we're on a really slow network, adding async to our JavaScript really helps us to get to that CSS and that DOM parsed as soon as possible, because the browser can complete all of the HTML parsing and then just throw DOM interactive and DOM content loaded and then hang out and wait for that JavaScript to come back and execute it whenever it comes back. The other option that we have is defer. So defer is very similar to async. It's going to wait to execute all of our scripts. However, when they come in, it's going to hold on to them, and then after the DOM is done, it will execute each of the scripts in order. So if you have a dependency order for your scripts where like they have to be executed in a specific order, then you need to use defer instead of async. Cool. All right, so before we move on to the next step of rendering, let's check in with our main thread. So as of now, our main thread has 4 different jobs. It has to parse the HTML, the CSS, the JS, and then it has to go off and execute our JavaScript. Now, I don't envy Shubi's team at all. Like, this is a really hard problem. I'm really excited to see how they're going to solve it. All right, so rendering, this is where the magic happens. Cool, so the goal for our rendering phase is that we want the browser to do less work. As with all of these, we want the browser to do less work. The render pipeline has these 4 different phases: styling, layout, paint, and composite. We'll start off with styling. So styling is actually pretty easy. Styling is where we take the DOM and that CSS DOM that we constructed, and the browser mashes them up together into another tree. Surprise, it's another tree. Firefox calls this the frame tree. Safari calls it render objects. Chrome calls it the render tree. So this is the point where the CSS in CSS, so the cascade, comes into play, because don't forget the browser has default styles and users can provide style sheets. But the browser will go through and basically take all of your CSS styles and match them up to the various nodes in the DOM and then say, okay, this is the computed style. So these, it's kind of like, I really like Lynn kind of talks about it as like a form that has a bunch of boxes that need to be checked out for, or checked off for every element about like its different CSS properties. And one thing to note is that any element that has display none doesn't end up in this tree. However, anything with visibility hidden actually gets put into the render tree. So this is going to be a really super important fact later, so remember that. Cool. All right, layout. Layout is another process where we create a tree. Yay! It's where we take that computed style tree and we actually figure out what all of the dimensions of the different boxes on screen are going to be. Now, I'm sick and tired of trees, so we're going to use a more visual representation. We're going to just imagine the screen has whatever dimensions the viewport has, and then the browser's going to go through each node and generate a new element or generate a new box to figure out what the size is. So we start with the body, and then it inserts all of the children with margins and padding, and then it figures out how tall the text is going to be, does that for our p tag, figures out how tall the text is going to be, and then we get to our div that wraps around our image, and ta-da. However, I don't know if you've noticed there, we don't have our image yet. The GIF hasn't come back over the wire because the GIF is taking a really friggin' long time because it's a really big GIF. So the browser can't actually calculate the height and width of the image. It's going to leave a little space for it for us, but it doesn't know the exact height and image. And this is another thing, hint, hint, this is going to come back and bite us. All right, moving on to paint. So let's talk really quickly about pixels. So what is a pixel? The way that computers figure out what to display as pixels on screen is very, very, very roughly, like a really simple mental model is that there's this thing called a frame buffer, which is essentially an array of arrays, and each child array has stored RGB and A values, and each one of those corresponds to the RGB, and then A is transparency for the little itty bitty lights that are in that one single pixel. Now, here's the thing about rendering. My privilege here is that I have an iPhone X, which has 2.7 million pixels on the screen. 2.7 million. Just think about that. Imagine how much time it takes to figure out all of these pixel values for 2.7 million pixels. It's crazy. Browsers are amazing. Computers are amazing. All right, so one of the ways that modern browsers help to reduce the amount of work it takes to render 2.7 million pixels on screen is that it actually will take all of those elements in our layout tree, and it will break them up into layers. Now, there are certain things that cause a new layer to be created. You can use CSS 3D transforms by adding CSS animation using opacity or transforms. You can use the CSS will change property, certain CSS filters, the video and the canvas elements, and then anything that's like a Z index above another layer will get put into its own layer. Now, layers are like super cool, and we're going to come back to layers actually when we talk about interaction. But for now, let's move on and talk about the final stage in the render pipeline, compositing. So our new best friend, we have a lot of best friends in the browser. Well, this is in the computer, but the GPU is awesome. So GPU stands for Graphics Processing Unit. These are things that are used very heavily in games. It used to be that most computers didn't necessarily come with GPUs, but nowadays most modern devices have them. And they're designed specifically for rendering pixels on a screen super fast. And again, Lynn gave a really amazing talk last year all about this. I highly recommend you go and find it and watch it, because it's like really fascinating. But basically, what the GPU does during the compositing phase is it takes our two different arrays of our two different layers, and then it does some math. So the math basically is a couple of things. It applies CSS transforms. This is like pseudocode in case that wasn't immediately obvious. So it applies our CSS transforms, it applies our CSS filters, and then it uses what's called a blend mode function to take the value of two different pixels that are on top of each other and calculate what the output value should be. So kind of like if you've ever used Photoshop and layers, there's like multiply, there's opacity, there's like a bunch of different filters. It's basically like a special math function that says, given pixel 1 and pixel 2, run it through a function, and then output what the final actual bitmap is going to look like. Cool. All right, so yay, we finally have something on screen. Oh, no? Okay. Although, you might notice we don't have our cat GIF yet. It's still coming out over the network. All right, so let's see where we are. So we're back in our first kind of crappy state, I apologize. But we've gotten up to our first meaningful paint. So let's see what happens now when you can see, so added on to the end of DOM content loaded, we have style, layout, and paint all happens on the main thread, and then compositing happens on a separate thread via the GPU. All right, so our cat GIF came back, but we're browser sad again, because now that our GIF is back, it's going to have to reflow. I'm sure you've all heard about reflow. People have mentioned layout, thrashing. We all know this is bad, but what does it really mean? So in this particular case, it means that we have to go through most of that entire pipeline all over again from scratch. Now, thankfully for us, we don't need to recalculate styles. However, we do have to relay out the entire page, repaint and recomposite in order to make space for that GIF, now that the browser knows how big it is. So we start off on the left with the layout, we figure out the GIF, and haha, you thought I was going to show you the GIF, but I'm not. I'm going to save it for the end. So it changes the height of the wrapping div of the GIF, that changes the height of the body. We have to make our new layers now. We use math, boo, and we smush our layers together, and now we have a bitmap that we can display on our screen. Hooray! Yeah. So you're probably saying to me right now, like, Katie, like, yeah, this sucks, but like, I mean, images come back over the wire. Like, I can't prevent that from happening. How can we stop it from reflowing? Well, it's a really simple thing. You just give the image dimensions. You can do it either in your CSS or you can do it in your actual SRC tag. I know with responsive images it's a bit harder now. We usually can't give it a straight pixel value, but simply by giving it, telling the browser how much space to leave for the image, we completely remove the need to relay out the page, and all it has to do is repaint and then recomposite. So it's not a full reflow. Awesome, right? Very, very simple change to make, and the browser's way happier. All right, so how's our poor main thread? Oh boy, we're up to 1, 2, 3, 4, 5, 6, 8 things that the main thread has to do. Poor main thread. However, we've discovered this really awesome fun thing, compositing, that happens on the GPU. So yay, let's composite more. All right, so now we have our page. And obviously our user isn't just going to look at the awesome GIF, because I'm not showing you the awesome GIF, but they're going to interact with the page. They're going to scroll, they're going to tap, they're going to do stuff. So let's talk about interaction and what happens then. So our goal for the interaction phase is that we want to be jank free. So again, we've already heard about jank and what jank is. So I'm not going to, thankfully I was able to delete a bunch of slides so I can actually maybe get in to snacks at some point soon, hopefully. But now we have this new job for our poor, overworked main thread where it has to handle user interaction. Now, Addie already talked about first input delay, so about when you're building the page and the user tries to interact with it and the user actions get queued up because they're waiting for all that other stuff that we just talked about to complete. But let's talk about something else, so we already know that. Let's talk about animation. So again, the basis for animation are these frames. If you think about a flip book, the browser kind of operates like a flip book, where every time you want to move something on the screen, the browser has to redraw the entire screen from scratch to show us an image that's going to move. And in order to be smooth looking animation, we want to have 60 frames per second, which divided means that we have 16.67 milliseconds to draw each frame. Cool. So our initial example didn't really have much animation or interaction in it, so this is our new example. So this is like a pretty typical pattern on the web. We have a button that opens up a dialog box. And as you can see, the main way that we're handling this is by using our accessibility properties to style our CSS, which is a really good practice to have to ensure that your site is accessible, is to actually style. Thank you, Eric. So we're using display none and display block. So what happens is when we look at our kind of timeline of frames, so every little pink line going up and down is 16.67 milliseconds. So the browser has to redraw 2.7 million pixels every 16.67 seconds. However, we click our button to open that dialog, and now the JS event handler fires, and that blocks our main thread for a little bit, so it can't re-render. And then it goes off and changes the style of the div from display none to display block, and that causes us to reflow, which causes jank. So you can see there's 4 different frames that we end up dropping because the browser's too busy doing all of these other things like handling the user input and handling reflow. It can't actually draw 2.7 million pixels. I can't get over that. It's just a number that doesn't make any sense. So back to our friends, layers. So layers are what's going to save us from this problem. Layers are really, really cool because it allows the browser to only repaint smaller areas of the screen when they change, and it doesn't have to actually go through and repaint the entire page. It also can move layers around, sort of like if you think about those old school overhead projector sheets, you can move them around in the drawing, or old school Walt Disney animation. So layers can get moved around and they can get smushed together, and it's math on the GPU that happens like that. So we want, actually, when we're doing stuff like that, to take advantage of layers. So really, in order to make this better, really all that we have to do is switch from using display none to using visibility hidden, because like I said, remember, if something is display none, it doesn't actually end up in our style calculation tree. The browser just discards it. So if we use visibility hidden, then the div actually stays in the DOM, or stays in the tree as we're building it, and we don't have to go back and recalculate that. And then if we use a CSS animation, then it's going to pop it onto another layer. So instead, this is what our timeline looks like. So we still have that little bit of time where we have to handle the JavaScript event. However, all we have to do is a little bit of restyling. We don't have to paint. We don't have to relayout. And then we pass it to the compositor, and it comes back super quickly with another frame. So, woo! All right. So I think we've all earned the right to finally see the best cat GIF ever on the planet. I hope you're ready. And if you can't see it, it's a cat is sitting there, and someone puts a little flower on its head, and it pulls its face back in like this disgusted face, and then someone animated behind it to make it look like it's jumping into hyperspace, and it is hysterical. Like, I crack myself up with this GIF all the time. All right, cool. So to recap, so how do we make our browser happy? Well, navigation phase, we want to just get that over with as quickly as humanly possible. Our parsing phase, we want to get to the DOM and the CSS OM as soon as possible, which allows the browser to start the most important phase, which is rendering. When we're talking about rendering, we want to do less work on the CPU. We want to try to offload as much as we can to the GPU. And then when we're talking about interaction, we want to make sure that we're jank-free so that users have a nice, smooth animation experience. So I want to say thank you to Addie, to Andy Davies, and Yoav Weiss, who sadly is not here with us, for answering a couple of my really deep internal browser questions. Thanks to Estelle for another awesome year. And thank you to all of you. And I just want to say I'm putting together a list of links. It's not ready yet. I'm sorry. I apologize. But I will tweet it all out along with the slides if you follow me at Sylor. Thank you.